Alright, so let's start. In the previous class, we looked at some examples of sub-Gaussian random variables. Right? So we of course know that the Bernoulli and the Gaussian random variables are sub-Gaussian. And we saw that any bounded random variable is also a sub-Gaussian random variable. And it's sub-Gaussian with variance factor which is proportional to the maximum of the absolute value that the random variable can take. Right? So all bounded random variables are sub-Gaussian, whether they're discrete or continuous. But we saw that the exponential random variable is not sub-Gaussian. The exponential, Laplacian, these random variables are not sub-Gaussian. They do have exponential tails, but it does not decay as e to the minus t squared. So we see that it's slower than a Gaussian, but still exponential nevertheless. In fact, the whole class of gamma distributions turns out to be not sub-Gaussian, but all of these still do have exponentially decaying tails. So we also looked at one particular application of concentration inequalities. Right? In the last class, I introduced this problem of dimensionality reduction, wherein you have m data points, and the goal is to reduce the dimension. These are high dimension. Each data point is basically a high dimensional vector. The question is, can you reduce the dimensionality of each of these vectors while at the same time preserving some property of this set of vectors? And in particular, the property that we wanted to preserve was basically the pairwise distances between any two points. So the goal was to design a map from a high dimensional space to a much lower dimensional space, such that the pairwise distance between every 2 points in this set is approximately preserved even after bringing it down to the lower dimensional space. And the claim was that it's indeed possible to do so. In fact, it's possible to do so using a linear map, and you can bring the dimensionality down from capital N to just order log n divided by epsilon square. So if n is something that is really, really large, you can, but n is not too large, and the approximation in the pairwise distances that you want is again not too small, you can bring it down to a much smaller dimension. Right? And in fact, independent of the dimensionality of the original space. Right? Question? Yes. Yes. Correct. That is true.
But there is data out of log instead of video. So that has a limit.
Okay, fine. That's true. Agreed, but typically, so here the assumption is that epsilon is some constant. So typically in these sorts of applications, you treat epsilon as a constant, but m and n are something that are allowed to grow. Alright? Or you allow epsilon to go to 0, but if you allow epsilon to go to 0, you are typically also allowing n and n to sort of grow to infinity, and epsilon decays at a sufficiently slow rate. That's generally the assumption. But yeah, like you have as well said, order log n divided by epsilon square, which is also perfectly valid. Even here, I mean, it's not just epsilon tending to 0, there's another point, which is if n is very, very large, right? For example, n is at least exponential in capital N, then the right hand side is still sort of linear or polynomial in n, which is not particularly helpful. You don't really get any reduction in the dimensionality. So really this entire result is helpful only when n is smaller than exponential in n, and epsilon is some constant or it decays at a sufficiently low rate. It could be some function of n and n, but it's not too small. So all of I mean, the results have to be interpreted in that particular form. Right? Okay. Also, side note is that this behavior or this dependence on n, m, and epsilon is known to be tight in the sense that even if I allow non-linear maps, it turns out that it is impossible to do any better than constant times log m divided by epsilon square. It would maybe improve epsilon square to epsilon square minus some polynomial in epsilon, but still it's still going to behave as constant times log n divided by epsilon square. That's the best, it's known that that is the best that can be achieved. Right? And the proof of the Johnson-Lindenstrauss Lemma, as stated here, it basically works in the following way. You pick a random matrix with IID Gaussian entries, and all with Gaussian with 0 mean and variance 1, and the linear transformation that you take is basically just 1 over square root of n times this matrix G bar. Right? And this matrix has the property that the norm of G times x is approximately equal to the norm of x, right? As long as n is sufficiently small. And when I say that the norm is approximately preserved, what essentially I'm saying is that if I fix a particular x, fix one particular vector x, and analyze the random variable obtained by taking g times x, y equal to g times x, then with high probability, the norm squared of y is going to be approximately equal to the norm squared of x. Okay. And in fact, I can control this probability, I can control the probability that this does not happen. Right? And as long as this probability is small, I can simply take a union bound over all possible x and basically get my result. So let's look at that a little more carefully. Right? So for now, let us assume that the probability that for a given x, so fix a particular vector x, we know that the probability, again the probability is to be taken over the random choice of g or g bar. So the probability that norm gx is greater than 1 plus epsilon times squared is greater than norm x squared, or norm gx squared is less than 1 minus epsilon times norm squared x is less than or equal to 2 to the minus some constant times n epsilon squared. Okay, so this is what I assume for now. We'll see how to prove this later. But let us suppose that this is indeed true. Then I know that for any pair of vectors, xy and xj, any fixed pair, the probability that gxi minus gxj, the norm of basically the pairwise difference with the distance between gxi and gxj, the probability that this is greater than 1 plus epsilon times the distance between xi and xj, or gxi minus gxj squared is less than 1 minus epsilon times the distance between xi and xj. This quantity is less than or equal to 2 to the minus some constant n epsilon squared. Right, so this is what I have. Now I want to know what is the probability that this happens for any pair in my given set. Right? So I'm given a set of vectors x1, x2 up to xm. I have m vectors, and I want to ensure that the pairwise distance between any two vectors after projection is roughly the same as the pairwise distance before projection. Correct? So I can ask the same question: what is the probability that this happens? So what is the probability that this happens for any pair xi, xj? If I call this set. Right, so this probability, I can just use the union bound. What can I say that this is less than or equal to? Yeah? Right, m choose 2 into 2 to the minus some constant, let me call this alpha, n epsilon square. Correct? Or this is less than or equal to m squared times 2 to the minus alpha n epsilon square. Now if I want this probability to be, say, bounded from above by, let's say, half, then how large should n be? Roughly. Log, correct, so log m square. So this quantity is less than or equal to half as long as n is greater than some constant times log m squared divided by epsilon squared, or n is greater than some constant times log m divided by epsilon squared. Right? So as long as n is larger than some constant times log m divided by epsilon squared, the probability of this bad event is strictly less than half. Okay? Or in other words, the probability that all the pairwise distances are approximately preserved is greater than half. Right? Which means that if I pick one uniformly at random, if I pick a g at random according to that Gaussian distribution, then there exists, the probability is greater than half, which implies that there's at least one g for which the distances are approximately preserved. It could be anything which is less than 1. Right? I just need the probability of the good event to be strictly positive, or the probability of the bad event being strictly less than 1. And half is something I just chose arbitrarily. Now I could demand something more. I could say that I want this to decay as 1 over m squared or whatever. Again, it doesn't matter. I'll still get the same behavior. Right? As long as all I want is, let's say, a polynomial decay in, let's say, n. So that is fine. In certain applications, this is enough. In certain applications, you may want a specific behavior for this particular, the probability of the bad event. You may want it to decay exponentially in n, or exponential, or let's say some particular behavior in m, in which case you have to choose the n more carefully. But as long as we are happy with the existence of one matrix which satisfies these properties, this is sufficient. Okay? Now, in this case, I chose G to be Gaussian, the entries of G to be Gaussian, but as it turns out, you can play with a much more wider variety of distributions. You can also choose G to be specific classes of structured matrices, and you still have this kind of behavior. As long as n is greater than some constant times log m by epsilon square, all the pairwise distances are approximately preserved. So dimensionality reduction can be done not just using Gaussian matrices, but you can also do it with a much wider class of matrices. Many of these techniques use similar tools, but not all of them. For example, if G is structured, then you need a completely different set of tools to analyze whether pairwise distances are approximately preserved or not. Okay. Any questions? Okay, so all that is left is to prove this particular statement. Right, the probability that this bad event happens, that the distance is not, or the norm squared is not approximately preserved, is something that is vanishing in n epsilon squared. Right? So we know that G is Gaussian. Right, so this is what we want to show. Right, but what did we say about expectation of norm Gx squared? We call this y basically, right? And we observe that each component of y is Gaussian, and the variance of y is basically the norm squared of x divided by n. Correct? So the norm squared of y is basically equal to the norm squared of x. Okay? And Gx squared, which is norm y squared, is the sum of independent random variables. Correct? Let me just right? I know each y of I is Gaussian, but here I have the square of a Gaussian. Is this going to be a sub-Gaussian random variable? Yeah? Okay, not necessarily. We know what the distribution of the square of a Gaussian is. Yeah, it's chi-square distribution. And is the chi-square distribution sub-Gaussian? Yes, you had it in the assignment, well, not the chi-square, but you had the gamma distribution. It's a specific case of a gamma distribution, so it's not sub-Gaussian. Right? So it's not sub-Gaussian. So y square of I is chi-square y of I is Gaussian between 0 and variance norm x squared divided by n. Right? But now you can just try to derive the moment generating function of the chi-square distribution, which you've already done in your assignment, right? Because you've derived the moment generating function of a gamma distribution. So you can derive the moment generating function of the chi-square distribution, and using that you can try to get the best possible Chernoff exponent, right? And again, just use the Chernoff bound and find the best lambda, plug in the best lambda, and you'll essentially be able to show that this is in fact right, because what is this? This essentially corresponds to the right tail, right? This is the same as saying probability that norm y squared is greater than 1 plus epsilon times expectation of norm y squared, or norm y squared is less than 1 minus epsilon times expected value of norm y squared, which is just the same as norm y squared minus expected value of norm y squared greater than epsilon times norm y squared. Right? You can just use the Chernoff bound and prove that this is less than or equal to 2 to the minus some constant times n times n. Okay, so I'll just leave this as an exercise. Right, just simple calculation, nothing more than that. Any questions? Okay, so now we saw that the gamma distribution of the chi-square in this particular example is not sub-Gaussian, right? So I couldn't use that tail bound directly. But still, when I use the Chernoff bound, I still see that the probability of the tail probability still decays exponentially in t, right? So this essentially corresponds to a larger class of random variables called sub-exponential or sometimes sub-gamma random variables. Right? So if you look at the class of gamma distributions, we know that they have an exponential tail bound, but it's not exponential in t square, it's exponential only in t. Right? So this corresponds to the gamma distribution. So if a random variable has a gamma-like tail, then it's said to be sub-gamma. Just like if it has Gaussian-like tails, it's called a sub-Gaussian distribution. So just as we had a set of equivalent conditions for sub-Gaussian distributions, we can derive similar equivalent conditions for sub-exponential distributions as well. Again, I will not prove all of these statements because it's very similar to what we did for the sub-Gaussian case, but we try to use this to derive tail. Right, so suppose that x is a random variable, then the following are equivalent. And as before, the corresponding constants essentially just differ by a universal constant. So for all I not equal to j, there is some universal constant C1, C2, such that Ki is at least C1 times Kj, and it's at most from C2 times Kj. Right, so these constant factors are off by some absolute constants. So the first condition is, again, you have probability. So a tail bound on the random variable. This is less than or equal to e to the minus p divided by k1 for all t greater than or equal to 0. 2 times this. Right? So it doesn't decay as e to the minus t square, but it decays just as e to the minus t. Any random variable that satisfies this property for all t is supposed to be subexponential. Okay? And the second condition, if you recall, was a bound on the moments. X to the p is less than or equal to, if you recall, what was the upper bound for sub-Gaussian random variable? What could you say about the moments? Okay, so the some constant times root p whole to the power p. Now the moments are going to be slightly larger. So k2 times p whole raised to the power. Alright, so you can sort of expect this because some Gaussian tails are where you have the decay being very fast. Some exponential tails basically decays exponentially but slightly slowly. Right? So naturally you would expect the moment to also be slightly larger. The moments don't fall that quickly. Right? The third property was, if you recall, we had a bound on e to the lambda square x square, right? Expectation e to the lambda square x square. But now we only make a claim about e to the lambda times absolute value of x. So this is less than or equal to e to the sum k3 times lambda, as long as small lambda is less than or equal to 1 over k3. Okay, and there is some constant k4 such that expectation of e to the absolute value of x divided by k4 is less than or equal to 2. Right. And the fifth condition was again a bound on moment generating function. So expected value of e to the lambda x is less than or equal to e to the lambda square k pi square. But this doesn't hold for all lambda greater than 0 because then it would be sub-Gaussian. But this holds only for lambda in a certain range. 1 over, let's call this k6. Alright. So the point is that all these 5 conditions are equivalent. So now let's suppose that X is a sub-Gaussian distribution. What can I say about X squared? Suppose that X is sub-Gaussian. If X is Gaussian, then what can I say about X squared? It's chi squared, and therefore it is sub-exponential. Right? It's not sub-Gaussian, but it's sub-exponential. But now if I take a general sub-Gaussian random variable X, can I say something about X squared? It's always going to be sub-exponential. Remember, if I can prove any one of these statements about the corresponding random variable X squared, then I'm done. So, here we define y to be equal to X squared. Alright? Second condition. Okay. Slightly easier, which comes almost 50. Okay. Yes, I can use again something even simpler. I can just use the fourth condition. Right? Because I know that if X is sub-Gaussian, then expected value of e to the X squared divided by whatever some k4 prime, this is less than or equal to 2. Right? But then y is equal to X squared. So absolute value of y is also equal to y equal to X squared. So expected value of e to the absolute value of y divided by k4 prime is less than or equal to 2. Right? Which basically implies that y is sub-exponential. Okay. What about the other way around? Suppose I have a random variable x and x square is sub-exponential. So take any random variable x and y equal to x square is sub-exponential. Can I say something about the random variable x? Can again use the same condition. I know that expectation of absolute value of y divided by k4 is less than or equal to 2, but y is just equal to x squared. So expected value of e to the x squared divided by k4 is less than or equal to 2, which must imply that x is sub-Gaussian. So this is a necessary and sufficient condition. If x is sub-Gaussian, then x square is sub-exponential. If x square is sub-exponential, then it automatically means that x is sub-Gaussian. So if you can, in some particular problem, if you can say something about the behavior of x or x square, then you also know how the other is going to behave. Right? But the one point to keep in mind is that sub-exponential is a much more general class. Right? Every sub-Gaussian distribution is also sub-exponential, but not every sub-exponential distribution is sub-Gaussian. Right? So, for example, let's take a bounded random variable x. If you look at x square, is this going to be bounded? If x is bounded, is x square going to be bounded? Yeah, it is going to be bounded. So x is sub-Gaussian. What about x square? X square is also going to be sub-Gaussian with a different variance factor, that's okay, but it's still going to be sub-Gaussian. But it's also going to be sub-exponential. Right? So just because x is sub-Gaussian does not mean that x square is not sub-Gaussian. It's guaranteed to be at least sub-exponential. Right? But on the other hand, if x square is sub-exponential, maybe not sub-Gaussian, you're guaranteed that x is going to be sub-Gaussian. Alright? Any questions?
Yes, every sub-Gaussian is not sub-Gaussian. Every sub-exponential is not sub-Gaussian.
Yes.
So what if we take a sub-Gaussian variable x and square it?
Okay.
That also is sub-exponential.
If you take
Sub-exponential variable x and square
yes,
it.
okay,
So we'll actually correspond.
so you are not guaranteed. So, for example, again I'm trying to make an example of, let's take the exponential distribution, right? So, just 1 second. So, let's take the exponential distribution, so that becomes e to the minus t, right? What happens, what would be the density function of x squared? Yeah? E to the power of minus 2t, I think. Think about it. My guess is that it should behave as e to the minus root x. Right? So something e to the minus root x times some constant. So this does not have an exponentially decaying tail, it's slower than an exponential. So it's not sub-exponential. Yeah, you got it. If it is sub-Gaussian, yes, it is also sub-exponential, but not necessarily geometric. That's right. The sub-exponential, the class of sub-exponential distributions is more general than the class of sub-Gaussian distributions. Basically, it contains the class of sub-Gaussian distributions. Correct. Correct. You could take root p, for example. That's fine. That's true. But we'll stop at p. Right? Basically, we want something to decay at least as e to the minus t. That's going to be our base limit in some sense. Any other questions? Okay. So, in fact, we can say something even stronger. Let's suppose that x and y are independent sub-Gaussian random variables. sub-Gaussian. So let's say X is sub-Gaussian with variance factor say V1 and Y is sub-Gaussian with variance factor V2. Then what can I say about X times Y?
We have to see.
Are you sure? Why? Again, so we predict that this is going to be sub-Gaussian or what should it? Again, why do you think that's what you're talking about?
Independent and the multiplier then we can multiply those expectations.
Okay, so let's take, again, let me get to, right? So the MGF is not the product of the MGFs in this case. Right, so what I'm interested in is expectation of e to the lambda times xy. I cannot factor this as a product of MGFs. But do I have any simple inequalities on xy? Okay, something even simpler. Okay, great. So let's say I have expected value of e to the lambda xy, which is less than or equal to expectation e to the lambda square, lambda times, let's say x square plus y square by 2, something even simpler. Okay.
So we will show x square e into y into y.
Correct.
Not e plus 2.
So how are you going to use Hender's inequality here?
Exact same say x y that's the product. Some x y is not equal to some x y power all power.
Sure.
Y
Okay, but that's still going to be slightly more complicated. Ultimately, I don't know what is expectation of lambda x to the power p for all p. Right? I only know, I have a handle on expectation e to the lambda x and expectation e to the lambda x squared, but nothing beyond. So, at least I'm not sure if a general Hender's inequality is going to give me anything. So here I'm just using sort of the basic inequality that x squared plus y squared whole divided by 2 is greater than or equal to x times square, right? Because x minus y the whole square is greater than or equal to 0. Okay, so I have this. But this is just equal to expected value of e to the lambda x squared by 2 times expected value of e to the lambda y squared by 2. Correct? Okay. What can I do now? Both of them are bounded, true. So, what can I say about this quantity? This is less than or equal to e to the lambda square. Sorry? Okay, so some constant times constant square by 4, let's say k1 square by 4, e to the lambda square times k2 square by 4. Yes? Sorry?
based on the third for subgroup.
Based on which it's lambda square. So this is true for lambda lying in a certain range. So it should be, so lambda should be less than or equal to 1 by k1. It should also be less than or equal to 1 by k2. So this is less than or equal to the minimum of 1 by k1 and 1 by k2. Let's see if this works. So this is e to the lambda square times k1 square plus k2 square divided by 4. But can I conclude anything based on this? It's can I
Put this down.
on which one? You mean from here to here? So I'm just using property 3 of sub-Gaussian random variables. The lambda, okay, fine, sure, lambda. Good. But can I conclude anything based on the properties that I have here? It's property 5, it is sub-exponential, right? Correct. So expectation e to the lambda x, in this case, expectation e to the lambda xy is less than or equal to e to the lambda square times some constant, as long as lambda is less than or equal to some other constant. One word. Something. Okay, so it is strictly positive. Right? So what this means is that xy is sub-exponential. Right?
If
If they are dependent, not in general. I'm sorry? Y equal to x square, what's true? Okay, if I have x and y, I have random variables x and y which are independent.
So can I take some of the product X or some other notion X?
Okay,
Definitely still divided into categories.
but how, so say I take y to be some f of x,
Such that it's still divided into
can that happen? There's a trivial case in which when that can happen, when f is just a function, just a constant value. But apart from that, is it possible to have y equal to f of x and still have x and y being independent of each other? Why? Yeah. Sure. Well, just look at the conditional PDF, the conditional probability of y given x. It's either going to be equal to 0 or it's going to be equal to. It's not going to be, if y is a non-trivial random variable, then the conditional distribution is always going to be a trivial random variable, but the conditional random variable is going to be conditioned on x equal to some particular constant, y is going to be a constant. Okay? Correct. So that's one special case, right? So I'm not saying that if x and y are dependent, then xy is not sub-exponential. The only point I'm trying to make is that in general, I can't make the claim that if x and y are dependent but sub-Gaussian, then xy is also sub-exponential. That's simple. Okay, so maybe this is a good point to stop. We'll continue in the next class. So there will be a quiz next week, probably next Thursday. I'll make a formal announcement in the Google class.